The railroad industry was one of the biggest leaders of the Industrial Revolution. The iron horse or the steam engine expanded our economic horizons immeasurably, and today our railroads are mostly in very good economic shape. But to say that all is well within the industry would be too generous. Although the industry has absorbed the benefits of communication technology, metallurgical improvements, welded rail, advanced locomotives, double-stack trains, computers, etc., it has made very few advances in one of its basic and most major functions, that of disassembling and rebuilding trains. Railroads can get a train from point A to point B very efficiently, but within their railroad yards there have been very, very few innovations. The state-of-the-art right now is the use of hump yards and remote control locomotives. But the flat switch yard is still the prevalent tool that is used to disassemble and reassemble trains. Each sorting method that the railroad industry uses relies on the switch. The railroad switch has been in use for about 180 years, and it has changed little other than to be modified to let it be operated remotely. It is a simple device, as this illustration shows us. It is a great device for redirecting a train or a block of rail cars from one track to another, but it is a nightmare tool for sorting individual rail cars. The switch is a maintenance nightmare as well, and requires a lot of cleaning of ice and snow in colder climates. And although switch heaters may be utilized in those locations, they are not very effective in drifting snow in heavy snowstorms. A switch is also very expensive. Inexpensive ones cost about $60,000 each, and a lot of them are required in a sorting yard or classification yard, as it is known in the industry. Let's look at other problems that are related to the railroad switch. Most existing railroad yards in this country were built decades ago, and as a result lack sufficient capacity to handle their current levels of business. One of the main reasons for the lack of capacity to sort railroad cars in rail yards is because when they were built, the average rail car was about 40 feet long. Nowadays, the average rail car is closer to 70 feet long. As a result, most classification yards are way too small to handle the number of rail cars that must be sorted in them. What happens when a railroad classification yard is too small? The major problem is that rehumps are created. What is a rehump? It is a rail car that must be sorted or switched 2 or 3 times or more to get it into its proper train. Many railroad yard managers boast that they have switched, for example, 1,800 cars in one day. But the sad fact is that due to insufficient capacity, perhaps 600 of those cars were handled 2 or 3 times to get them to the proper track. Can you imagine a manufacturing facility that boasted that 1/2 of its production had to be done twice? No, of course not. Such a facility would be enlarged or something would be changed. A person like Henry Ford would not have stood for that kind of inefficiency, nor would any good manager in any industry for that matter. And there are other factors that create rehumps. In hump yards, anti-cornering software also creates rehumps. In flat yards, crews miss a switch or read a switch list wrong, and cars are sent to the wrong track. Frequently, yard masters, the managers who decide which track to use to put rail cars to build a train, have to send a number of cars to one track and mix them because of lack of capacity. As a result, rail cars are delayed, and customers wonder why the railroad doesn't have any speed and service reliability. Is it any wonder why? With a lack of yard capacity and the industry's reliance on an antiquated tool for sorting rail cars? Let's look at some of the problems that the use of the switch creates. Because railroad yards are configured the way they are, only one train in each yard can be sorted at a time. The rest of the trains wait their turn to be sorted. This creates a great deal of missed connections to outbound trains and a lot of shipper dissatisfaction. Also, switching in rail yards is a very dangerous activity. Each year, about 25 employees are killed in rail yards in the United States. That doesn't even consider the number of people who are seriously injured. If 25 people were killed in one day in a single accident, the public would be in an uproar to shut the industry down. But because the fatalities are spread around the country over time, it doesn't receive much notice. Putting people on, under, and around moving rail cars that weigh tons, even when unloaded, is a recipe for disaster. The most ironic statement that I can make about sorting or switching rail cars is that for 180 years, the railroad industry has been doing the central and integral function of its business backwards. Rather than have rail cars under control at all times and couple them gently, railroads launch them. And due to not being able to accurately control the speed of launched cars, they usually couple into each other at too great a speed, or at insufficient speed for them to couple together. Let's examine each method of sorting railroad cars that is in use today. The hump yard is the railroad's most productive and manpower-efficient method of sorting rail cars. Please note the drawing of a cross-section of a hump yard. A train is pushed up a hill. Cars are uncoupled at the apex, and the cars roll by gravity to a coupling unless, of course, the rail car doesn't roll far enough to make a coupling. When that happens, the hump engines go down and shove the car to a coupling, or a crew at the other end of the classification yard couples to the car or cars and pulls them down. While a crew does that from the pull-out end of the yard, the track is blocked out to protect them. And when that happens, if another car is humped for that track, it is diverted. And guess what? Yes, you get a rehump. The rehumped car will have to be sorted again. The industry has spent hundreds of millions of dollars trying to properly control the speed of cars as they couple into each other. To date, nothing has really worked well. The ideal speed for rail cars to couple is 3 miles per hour or less. Also, the ideal situation is that cars roll off the hill and go far enough to couple to the car that preceded it into the proper classification track. This needs to occur all the time without fail. There is no railroad in the country that is capable of meeting these standards of control. Why? Because the railroad switch is the tool that is used. The drawbacks to the hump yard are many. Diesel fuel is burned in the locomotives, creating polluted air. Strong diesel locomotives are required to hump cars, and they are very expensive. To control the speed of each rail car as it is launched down the hump, car retarders are used to squeeze the wheels of the car to slow it down. While slowing the cars down, retarders may emit noise up to and exceeding 120 decibels. One of the worst features is that an immense area of land is underutilized for the sorting of the cars. Look at all the land that is wasted because of the use of the railroad switch. Later on, I will demonstrate to you how this area of land can be utilized to help railroads increase their land utilization without having to buy more land. On the other end of a typical hump yard, retarders are required on the other end of the classification yard to keep cars from rolling away. That results in another expense and more noise. How productive are hump yards? Although hump yards can theoretically hump 3 to 4 cars a minute, one would expect to hump 14 to 1,900 cars per shift. In reality, because of the physical and policy problems inherent in their design and operation, hump yards do well to process 600 cars per shift, less than one-half the productivity one would expect. Nevertheless, hump yards with all their drawbacks are the most efficient yards in terms of sorting rail cars quickly. Most railroads in the USA use the flat yard, given the name because they are laid out on a generally flat surface, although there may be a depressed area in the middle of the yard so that rail cars will not roll out at either end. But because the sorting of the cars requires switches, vast amounts of space are wasted, just as with hump yards. Also, because most switches in flat yards have to be operated by hand, a large number of people are required to sort the cars. Again, diesel engines are used, and their fuel creates pollution. The locomotives are expensive. Many more people are used in flat yards than in a hump yard. Productivity is poor in flat yards. Because the coupling speed of cars is pure guesswork, the rail cars, their contents, and the track structure often are damaged. The result is enormous cost and customer dissatisfaction. In an effort to cut cost, The railroads are using many remote control locomotives, essentially moving the engineer from his seat on the locomotive and putting him on the ground. He uses an electronic box to control all the functions of the locomotive that he previously performed in the cab of the locomotive. There is no question that the remote control operator is safer on the ground than in the locomotive. Studies have proven that. But the remote control operator is still faced with the same dilemma on the ground as he was in the cab of the locomotive. His engine is working in a rail yard whose operation is tied to switches. And like in a flat yard, people are required to operate all of the manual switches. The same seesawing back and forth to sort the cars in the rail yard is still necessary, and approximately the same number of cars are sorted. The method of sorting has the same drawbacks that the other two methods do: risk to life and limb, diesel usage, diesel fume pollution, damage and delay to the customer's freight, damage to the rail cars themselves and to the track structure. Remote control locomotives are in widespread use in the railroad industry, and they are excellent for handling large blocks of rail cars, but they do little to aid sorting rail cars other than by reducing personnel. Each sorting method uses the railroad switch to redirect one rail car from one track to another, but each of these methods of sorting rail cars is inherently inefficient. Remote control locomotives reduce personnel, but they are extremely inefficient when it comes to switching cars. Hump yards, as huge as they are, rarely process more than 1,800 cars in a day. Let's look at all the problems that most railroad yards have in common. In a rail hump yard where a process control computer system controls the switching of the rail cars, average coupling speeds may approximate 4 miles per hour or less, but the standard deviation is wide and many rail cars couple to each other at 8 miles per hour or more. I have personally witnessed a 21-mile-per-hour coupling, verified with radar. What do hard couplings do? Immediately or eventually, they damage the physical components of rail cars. Railroads spend hundreds of millions of dollars annually repairing damaged rail cars. But the hidden damage in hard couplings is also that when two rail cars collide, the contents of the car take a beating, and our customer is outraged when he finds that his precious cargo is damaged or destroyed. The track may be punished as well, to the extent that the rail may be rolled over and the railroad car derails, stopping or slowing down the switching process. And when winter arrives in the northern climates, switches fill with ice and snow, and operations slow down considerably. The side frames of cars drag in heavy snow, making switching even more difficult and unpredictable. It is incredible that our railroads do as well as they do, considering that one of their most basic functions, switching, has hardly evolved in 180 years. Until now, that is. What I am going to show you today is a new methodology to sort railroad cars. It uses the concept of robotics to displace the dangerous, inefficient, and costly way trains are disassembled and reassembled. Most modern industries have looked to robotics to solve many of their problems. There is no reason why railroads shouldn't do so as well. Here's a photograph of a model of the robotic yard. In this photo, the 3 inbound tracks in the receiving yard are full of cars. Please note that the cars are different colors. Our job is to sort them by color, the same way that they would be sorted according to their destination. Let's say that the brown cars are destined for Chicago, the green cars for Fort Worth, the cars with the red tops for Los Angeles, and the cars with the white tops for Memphis. In a railroad yard, our job would be to put all the cars going to the same destination in the same track. Note that there are 2 yellow rectangular objects resting in a depressed area that we will call the pit. We will refer to these objects as transfer tables because we're going to use them to transfer cars from the inbound tracks to the destination tracks. There are 3 tracks on top of each yellow transfer table, and the transfer tables are aligned with the inbound tracks. The tracks to the right of the screen are the classification tracks where the cars will be sorted by destination, or in this illustration of the concept, by color. In this photo, a series of 3 rail cars have been loaded onto the first transfer table. Indexers move them onto the table. Rail car indexers come in a variety of configurations. They can be stationed on top of cross ties and shove against the axles of the car, or they may be positioned next to each track and push against the body of the car. There are a variety of robotic rail car movers that have been in use for years, all for the purpose of handling railroad cars without using locomotives. Here, the first 3 cars are moving perpendicular to the classification tracks, and the next 3 cars will be loaded onto the second transfer table as soon as the first table is in the clear. The process continues as the first table offloads the cars onto their proper classification track. Meanwhile, the second table is in the process of offloading its cars. Please note that the distance from the inbound tracks to the classification tracks has been greatly reduced. Both inbound and class tracks are now as close as possible to each other. In this photo, the process moves forward with both transfer tables in use. The cars are moved up at up to 3 miles per hour by the transfer tables, and the cars are moved into the class tracks, where they couple together at a speed of 3 miles per hour or less, because they're under constant control by the rail car indexers. This gentle handling ensures that cars are not subjected to rough handling and that the contents remain undamaged. As a result, railroads will be able to recoup some of the fragile products they previously carried. As the process continues, the cars are lined up in the proper tracks. Because they will be coupled together during the sorting process, a locomotive and employees will no longer be required to go into the track to couple the cars together. This will eliminate a very dangerous work activity and will save lives and prevent injuries. Also, because the class tracks have been lengthened, the capacity of the classification yard will be significantly increased. And, as was mentioned, the whole process will treat the cars with care. You may be wondering what the single track on the other side of the pit is for. Actually, the whole other side of the pit could be used for a class yard. In this instance, it will illustrate how hazardous material cars will be treated. Let us pretend the white-topped Doritos car is filled with explosives. The Federal Code of Regulations does not allow cars containing explosives to roll freely and collide with other rail cars. As a result, railroad sorting operations are slowed considerably while explosive cars are shoved to a coupling by the train that is being sorted. It is a very time-consuming process, and while it is going on, no other rail cars can be sorted, resulting in a significant loss of productivity. How significant is the difference in productivity between a state-of-the-art hump yard and a robotic yard? The best hump yards may be able to sort up to 1,800 cars per day. Simulation of the robotic yard indicates that it will be capable of sorting over 4,400 cars per day, an increase of over 140%. This means that the amount of time that rail cars will spend in yards will decrease dramatically, making the railroad industry much more competitive with trucks. Shippers will see their freight move faster and more predictably. Let's continue now with the innovative sorting process. Note that our white-topped explosive car has passed its destination track. Note that the brown rail car is lining up to go to its proper track. And in this photo, it is moved by the indexers for coupling with the other brown cars. The table moves back toward a position of alignment with the single hazmat, hazardous material track. The sorting of all the inbound trains is now complete. Our explosive car will be put with the other white-topped cars later by our system. In the track with the white-topped cars, we will have to process 3 more cars before we can put the car of explosives in the train. Because federal law requires that cars filled with explosives cannot be placed closer than the 6th car from the trailing locomotive in a mainline train. The robotic yard overcomes many of the problems with the current ways that rail cars are sorted. 1. Because no people are required to sort the rail cars, death and injury to employees engaged in the sorting process are eliminated. 2. No locomotives are needed. Cars are moved by rail car indexers. Costly locomotives don't have to be purchased and maintained. 3. Because no locomotives are needed, diesel fumes from yard switch engines are eliminated. 4. The rail cars are in constant control and never exceed a speed over 3 miles per hour. The result? No damage to the rail cars, the track they roll over, or to the customer's freight. 5. Rehumps are eliminated because the wasted space in flat yards and hump yards is eliminated by using that space for extension of the classification tracks. Here is how that is accomplished. The wasted space is caused by switches. When the switches are removed, either or both the classification tracks can be lengthened. 6. All of the sorting operations take place on straight track. As a result, bypassed drawbar derailments are eliminated. Also, even if a derailment does not occur, damage to knuckles, drawbars, and other components are eliminated. Damage to track is substantially reduced. 7. Because current methods of sorting allow a rail crew to sort only one train at a time, trains back up in the sorting process. The result is that rail cars stay in most rail yards about 28 to 32 hours or more. By speeding up the sorting process, rail cars will get to their destinations more quickly, and the time they dwell in rail yards will be substantially reduced. Savings on the rental of rail cars will be enormous. 8. Finally, because the classification tracks can be lengthened and all cars coupled during the sorting process, trains can depart from the class yards rather than be pulled out of the class tracks and inefficiently shoved to another one to build a train. Usually, when technological advances need to be made, the expense can be considerable, but eventually the cost is overcome by savings, if the savings produce a significant rate of return on investment. Does the robotic yard create savings? You bet it does, and the savings are enormous. We gave executives of a Class 1 railroad a presentation of the concept of the robotic yard and asked them to tell us how much savings would accrue to their company if this concept were applied in their rail yard. They analyzed the savings that would accrue to their operations if this concept were applied at their 12 most efficient yards, hump yards. A quick analysis indicated that the company would save an average of $8.8 million annually at each of these facilities. The savings would recur year after year, but the savings were understated because a number of factors were not included, such as fringe benefits of 65% of each dollar spent on wages. Nevertheless, at a savings of $8.8 million at their 12 most efficient yards, and with 70 total yards on their railroad system, a recurring annual savings of $616 million will be achieved year after year with implementation of this concept on their railroad. And this is a conservative statement of savings. The savings are probably closer to $900 million per year. Where does our company, TRY, Railroad Engineering Services, LLC, go from here? Incidentally, the TRY stands for the Robotic Yard, and our company is doing business at TRES, LLC. We are seeking partners in the form of railroad suppliers or railroads, and private funding and or government funding to bring this concept to reality. Our goal is to build a small, full-scale prototype of the robotic yard to prove that the concept works. When successful, this innovation will revolutionize the way railroads operate, not just in the United States, but globally. The benefits to railroad shippers will be enormous. And finally, our railroad system will be competitive with the trucking industry. Railroads will move freight safer, faster, more reliably, more efficiently, and cleaner than they have ever done in the history of the industry.